Good day, I'm Maile Madziba. Welcome back to our channel. Today we are continuing with our CIR 211 module. And CIR 211 module is the second year chemical engineering module at the University of Pretoria. Today we're looking at tutorial 4 and we are looking at question 3 of tutorial 4. It says a mixture of CO2 which is 40% and H2 which is 50% and He which is 10% must be heated from 20 degrees Celsius to 70 degrees Celsius. The gas mixture is set at a pressure of 15 bar and the flow rate is 0.92 kilomole per second. What power output in kilowatt hour is required from the heater if 10% of the heat is lost? Let me just cancel this here so there's no confusion. So it says what power output in kilowatt hour is required from the heater if 10% of the heat is lost. So we are given Cp there. So well, this is actually the standard Cp equation is Cp plus 8 Cp equals to A plus Bt, and we are told that the units are in calories per gram mole Kelvin with T in Kelvin. So we have the constants here. We have for CO2, A is equals to 6.39 and B is equals to 1.01 times 10 to the power minus 2, and with the molar mass is 44. So with this constants here, we can actually calculate the Cp for all these values. So we can just say, therefore, Cp for CO2 is equals to, because A for CO2 is 6.39, so it's 6.39 plus B for CO2 is 1.01 times 10 to the power minus 2. Then we can have our T, and then we can just put in bracket here that the units are in calorie per gram mole Kelvin, and also with T in Kelvin. So this is actually the Cp value, the Cp equation for CO2, and then now we say the Cp for H2. So the Cp for H2 then becomes the A for H2 is 6.42 plus the B is 0.104 times 10 to the power minus 2 T, and equally also the units are the same, is calorie per gram mole Kelvin. Let me just put them in bracket, and then with T in Kelvin. So all the Cp's are taking this format. So now the Cp for helium H2 is equals to the constant for the A for He is 4.97, and it's important to note that the B for He is actually 0. So which means okay, let me just put it properly. Which means this part, the Bt part here for He is not there. And with that said, because that means the Cp for He is actually a constant, and with that said, we can just say calorie per gram mole Kelvin. So we don't really need to put with T in Kelvin because it's actually a variable. So there's no variable here, it's actually a constant. And with that said, when we have all the Cp's in place, then we can continue to solve the equation. So an important part we need to do is to understand that we are given a flow rate of 0.92 kilomole per second. So we can just choose our basis. So we can just say basis, right, is equal to 0.92 kilomole per second, right, of the mixture of the CO2, H2, and He mixture. So this actually 0.92 kilomole per second of the CO2, H2, and He mixture. And if that is the case, then it's important that we calculate the individual number of moles of all these gases. So with that said, we can just say, okay, the number of moles of, let's start with CO2. The number of moles of CO2, we are told that out of the 0.92 kilomole per second, our CO2 is actually 40%. So the number of moles of CO2 is equals to the total, which is 0.92 kilomole per second, right? Multiplied by the mole fraction, which is 0.4. And then if you use your calculator, that gives you 0.368 kilomole per second. So this is actually a CO2 flow rate. And because now, if you check the CPs are expressed in gram mole, it's just important that we convert this kilomole per second to gram mole per second. So we can just say it's equals to 368 gram moles per second. This shouldn't be difficult. This because from kilomole per second to gram mole per second, you simply multiply by 1,000. So it shouldn't be something difficult. Then we go to our H2. So we say the number of moles of H2 is equals to 0.92 kilomole per second, which is the total kilomole, multiplied by, from the problem statement we are told that our H2 is actually 50%, so the mole fraction will be 0.5, and when you use your calculator, that's gonna give you 0.46 kilomole 0.46 kilomole per second, right? And with that said, we can easily convert this to gram moles per second, and if you do that, that gives you 460 gram moles per second. Now coming to the number of moles of our He, which is our helium, so then we do the same. We say 0.92 kilomole per second multiplied by, and from the problem statement, we know that the helium is actually 10%, so we can just say multiply by 0.1, and if you use your calculator, it gives you 0.092 kilomole per second, right? And if you convert that to gram moles, then it gives you 92 gram moles per second. So now we have the flow rates of all the three gases in the mixture. So now, with that said, it takes us to actually our second step, or another step, and now we're going to be calculating the change in enthalpy. Let me just bring the problem statement again. They say, what is the power output in kilowatt hour? What power output in kilowatt hour is required from the heater if 10% of the heat is lost? So the 10% of the heat is lost is something that we're going to consider later. So we first need to calculate the power output that is required to actually heat the mixture of these gases from 20 degrees to 70 degrees at this flow rate and with this quantities in the mixture. So with that said, now we're going to need to calculate the change in enthalpy, because for us to get the power, you actually need to calculate the change in enthalpy. For us to calculate the power output of the heater, we need to calculate the required change in enthalpy individually of all these three gases that is required to move all these gases from 20 degrees Celsius to 70 degrees Celsius. So we're gonna start with, let me just write here that from 20 degrees Celsius to 70 degrees Celsius. So we're gonna start with our CO2 rather. So you can just say change in enthalpy of CO2. We know the general equation is T2 Cp dt. So this is actually the general equation, and the Cp here is the Cp of CO2, and the number of moles is actually the flow rate of CO2 also. And with that said, we can just plug in more values and say it's 368 gram moles per second, right? And then we know we're gonna integrate from 20 degrees to 70 degrees. So, and then we are told that the temperature is in Kelvin, so we're gonna convert the degrees to Kelvin. So it's 293.15 to 343.15, right? So, and then we can just plug in. Remember the CP value, we have the CP of CO2. We did make arrangements or calculations for it. Is 6.9, is 6.39 plus 1.01 times 10 to the power minus 2 t, right? And we need to put the dt at the end just to show that we are actually integrating. And this is equals to, if we do those integrations, and this then gives us 368 gram moles per second. It's important to understand that this is actually a constant, it's not changing. So, and then we integrated. We know 6.39, when you integrate it, it becomes 6.39 t plus 1.01 times 10 to the power minus t. The t becomes t squared, and then you have to divide, and then we have the dt falls off. Now our substitution temperature, we can plug it here even though we haven't substituted yet. So it's 343.15 Kelvin, right? And this is equals to 368 gram moles per second, and then we do the substitution. So it's 6.39. The T, we substitute the two temperatures, so it's calculus 158 now. 343.15 minus 293.15, right? Plus we do the same here, 1.01 times 10 to the power minus 2, right, all over 2. Now the t, we substitute 343.15 squared minus 293.15 squared, right? So yeah, that becomes it. And then we can just add an additional step just for clarity purposes, 368 gram moles per second, and then this gives us 319.5 plus 160.6657, right? And well, this bracket here, the unit of this bracket is calorie per gram mole. This is because the general units that were calorie per gram mole Kelvin have been cancelled as a result of plugging in the temperature. But I think it will take a formal calculus module to actually understand that. So here I just had to explain it briefly. So, and then that is equals to, now remember you still have the constant of gram moles per second. So the gram moles cancel the gram moles, and we are left with calories per second. And if you use your calculator, that gives you 176700.996 calories per second, right? So now by this stage we are done with the change in enthalpy, calculating the change in enthalpy of the CO2. Then we go to the change in enthalpy of the H2. We do the same. We know is equals to, we know it's N. Let me just rewrite it, T1, T2, CB, dt. And then if you do those calculations, you know those substituting is 460 gram moles per second. And then we integrate from 293.15 to 343.15, and then we know the CP of H2 is actually 6.42. We calculated it earlier, 6.42 plus 0.104 times 10 to the power minus 2t, right, all dt. So this is actually the change in enthalpy of H2, right? So now let's go to the next page. So now we need to make sure that we do the calculations necessary here to simplify this. So with that said, that means we know when we move from there, we're gonna have to integrate. So it's gonna be equals to 460 gram moles per second, right? Our 6.42 becomes 6.42 T because now we are integrating, right? And then plus 0.104 times 10 to the power minus 2 T squared all over 2. And our dt falls off. Now we are left with our substitution temperatures is 293.15 to 343.15, right? So that becomes that. And if you do further simplification, we have 460 gram moles per second, right? And then we can just do the substitution here. We know our 6.42, then we substitute the temperature is 343.15 minus 293.15 plus 0.104 times 10 to the power minus 2 all over 2. And then our t squared, we then substitute 343.15 squared, right, minus 293.15 squared, right? Yeah, so that becomes, a more simplified format after we did the integration. And then this is equals to 460 gram moles per second, and then we are left with 321 plus 16.5438, right? We have integrated and simplified this, and we know that the units for this is actually calorie per gram mole, because now that we have integrated, the temperature fell off, and when we reach here we can cancel the gram moles, and if you use your calculator, that gives you 155,270.148 calories per second. So by this time we are done calculating the change in enthalpy of H2 from 20 degrees to 70 degrees at that particular flow rate. So now we are left with the change in enthalpy of our H2, so of our HE, rather, the helium. So we go to the change in enthalpy of HE is equals to, I just need to explain something here. Let me bring the original the problem statement. You see, when we have a constant change in enthalpy, we don't need to do integration. Though conceptually and mathematically it's actually an integration been done, but because it's a constant, there's a straightforward equation where the integration has already been done to us. So we know that we can just say it's NCP delta T, right? So the NCP delta T is actually I don't know if I should explain this, but it's actually after integrating, but because there's no variable in it, so the integration is actually much more easier. So for instance, if we were to have, like, let me bring it, like 4.97, if you were to integrate it, it would be, where is it? 4.97 T, and 4.97 T, when you integrate it from these two temperatures, it just, you're just going to be multiplying the change in temperature, because you're going to be saying 343.15 minus 293.15. So it's basically the same thing. So because it's a constant, so it shouldn't be a problem. This is because maybe somebody might be confused that why in the first two gases we did integration, and here we didn't do integration. There's a straight, because it's a constant, there's a straightforward equation that we can use, but mathematically there's actually an integration that has already been done for us, so we just needed to substitute the equations. So I hope that is clearer. So moving forward, then we get to, okay, so we know it's NCTTT. The number of moles of N is actually 92 gram moles per second. It's 92 gram moles per second multiplied by our CP is 4.97, and because it's 4.97 as a constant, then we just plug in the unit calorie per gram mole Kelvin, right? Multiplied by the change in temperature is 343.15 minus 293.15, right? And if you use your calculator, it gives you 22862 calories per second. So this then becomes the total, the change in enthalpy of the helium at that particular flow rate in those conditions. So with that said, then we can calculate the total change in enthalpy. Total change in enthalpy is equals to the enthalpy of CO2. Change in enthalpy of CO2 is 176,700.996 calories per second, plus the change in enthalpy of the H2 is, we calculate it to be 155,270.148 calories per second, plus the change in enthalpy of the helium is 22862 calories per second. And if you use your calculator, it gives you 354833.144 calories per second. So now remember the question, they say what is the power output in kilowatt, or what power output in kilowatt is required from the heater if 10% of the heat is lost. So first of all, we need to understand, there are two things I want to explain out of the statement. First of all, we have the change in enthalpy in calories per second. So we need to first convert this change in enthalpy from, we can either convert this change in enthalpy from calories to joules and calculate based on a 10% loss, or we can actually calculate all this based on a 10% loss and then only convert to kilowatt hours later. So I think the easiest way is to actually calculate the 10% loss from here. So with this said, because we are told that what is the change in enthalpy in kilowatt, what is the power output of the heater if 10% is lost, for us to get that, we need to first calculate the total amount of total amount of power that is required to heat the gases mixture from 20 degrees to 70 degrees, right? And this is actually the total amount of the enthalpy, or the power. This is actually enthalpy and power. It's not, especially calories per second. How do I explain this? I want to explain that the change in enthalpy is not so much different from the power. It's just that, remember, the enthalpy here is in calories per second. We can easily convert the change in enthalpy to joules per second, and we know joules per second is power. So basically here, if we're to convert the calories to joules, then we have reached the joules per hour. Rather, we have reached the joule, the joules per second, and joules per second is the power. So before we do that conversion, I want us to consider the fact that they said there's a 10% loss of the heat. So before we convert to the power, let's first deal with the 10% loss, right? And this total enthalpy here is the total enthalpy required to move the temperature, or to move the gases from 20 degrees to 70 degrees. But it doesn't take into consideration the loss, right? So now we're going to calculate the total enthalpy when considering the 10% loss from the heater. And after we got that change in enthalpy with the 10% loss included, then we can easily convert to power. That would be easier. So converting to kilowatt is going to be the last part. And for us to convert to get the change in enthalpy with 10% loss, we can simply use a simpler approach to say let x be the total output of the heater, right? So let x is the total output of the heater, but we know that 10% of the amount that leaves the heater is actually lost, right? So we can just say x, which is the total amount of the heat from the heater, or we can even call it enthalpy from the heater, minus 10% of the total. And so we can say minus 0.1x. This is because 0.1 represent 10%. So is the total minus 10% of the total is equals to the enthalpy required to move the gases from 20 degrees to 70 degrees. So it's equals to 3.144 calories per second. Again, therefore 0.9x is equals to 3.144 calories per second. Therefore, our x is equals to 39,4259.049 calories per second. This is the total energy that the heater needs to heat, and then that is going to be able to move to heat the gases from 20 degrees to 70 degrees and include the 10% loss of the heat that is leaving the heater, right? So that is actually the case. Now when we have the x, or the total energy leaving the heater, in calories per second, we can simply convert all this from calories per second into joules, right? Rather from calories per second into joules, because we know that calories we have a ratio of calories and joules. So we can just say, therefore x is equals to 39. Is it still visible? Yeah, it's 394259 394259.049 394259.049 calories per second multiplied by, we know that 1 calorie is actually 4.187 joules. So we can just say 4.187 joules all over 1 calorie, right? And if you use your calculator, that will give you let me verify here, that will give you 16,50726.6382 joules per second. I hope it's visible, right? Or let me just bring it here and say x is equal, well, let me put this here. I hope it will be visible. X is equals to, when you multiply this by this, x is equals to 1650. My hand is tired, guys. That's why I'm not able to focus that much, but I'll try. I'm almost done. 1650762.6382, right, joules per second. And we know joules per second is power, so it's basically, so we can just divide this by 1000, because joules per second is power. We can divide this by 1000, then becomes the kilowatt, right? So we have 1650.7626 kilowatt. I hope I hope it's more visible. This is actually the final answer, 1650.7626 kilowatt. So this is actually the answer that they are requiring here when they said, what is the power output in kilowatt hour? What power output in kilowatt hour is required to heat the mixture of the gases if 10% of the heat is lost. So this is actually the power that is required that the heater must release, and after it releases this and 10% of this is lost, then the remainder of the power is actually the amount that is required to heat the gas mixture from 20 degrees Celsius to 70 degrees Celsius. I'm so tired, guys. Sorry about that. Thank you for this time, and I hope we meet again in our next video.